All right, so we're going to do a little crash course slash, kind of full-blown lecture on the muscular system. So I'll try to be moving through pretty quickly just to make sure we address all the topics relatively fast and, highlight the main things about the system and go over, and briefly touch over some of the smaller details. So the first thing we do with any physiological system when we get into it is to always make sure we know and understand the functions of the system. So I have this presentation specifically listed as questions, so you can write these questions and then fill them in on your own. So what exactly are the functions of the muscular system? Well, first and foremost, movement. Our predominantly we look at the skeletal muscle tissue, at least in this course, where obviously that's attaching to our skeletal frame, which then produces all the movements that we see at our joints and do throughout our normal activity. However, all different types of muscle tissue, which we'll learn about, smooth and cardiac, do produce movements, right? Our cardiac tissue, the heart, pumps the blood and propels the blood through the body. And then we do have smooth muscles in the organs and, vessels, blood vessels, to name one, in the body that also help to move substances through it. So alongside with the skeletal muscle tissue, to keep our bones and joints in place, that maintains our posture and our positioning. Everybody right now is using some form of muscular contraction, aka tonus, in order to create and keep your body in the position that it is. Whether you're sitting, standing, leaning, whatever, your muscles are engaged right now to keep yourself in that position. And then lastly, heat production. As we're going to learn, the product of muscular contraction requires that we break molecular bonds, turning adenosine triphosphate into adenosine diphosphate. We'll take a brief look at that, which then that breaking of the chemical bonds creates a lot of heat. And so a muscular contraction, muscular movement and activity generates heat. So posture, we briefly touched on. What exactly is posture? Just to take a quick understanding of it, is the position that the body assumes over a base of support. So the base of support is kind of the key thing we want to focus on and understand, which is whether you're sitting down, the base of your support would be, your ischial bones, the ischial tuberosities, your sits bones, or if you're standing, or if you're on a headstand and your palms are what's holding you up, that is your posture, and you're assuming that position over that base of support. So when we do things such as assessments like static postural assessments, right, we want to take note of, one, the base that they're standing over, whether they're sitting or standing, and then assess the symmetries of the body from there on out. And of course, we'll talk about assessments, later on in another video. But our next question comes up is, what is tonus? So a follow-up from posture is that, well, muscles maintain what's called a partial contraction or tonus in order to keep those muscles in position. So like I said, you sitting and holding your position right now, your muscles are engaged to some degree to create that tensile force in the muscles to maintain where they're at and keep the body in its proper positioning. We call that muscle tone or muscle tonus. So muscle fibers. Muscle fibers are the individual cells of this lecture. So when we look at the physiological systems, we do briefly touch on histology, the science of cells, and talk briefly about what those cells do, what they're responsible for. So in this case, a muscle cell, muscle fiber, is the basic cellular unit that makes up muscle tissue. Now, there are different types of muscle cells, as we'll learn that skeletal muscle fibers, cardiac muscle fibers, and smooth muscle fibers do differ from each other. And we're going to take a bigger look at the skeletal muscle fibers in this lection in particular. So the muscle fibers, the cells of this system, aren't very unsimilar to any of the other cells we've seen in previous lectures. So just as we learned in chapter 18 and other various lectures, that cells contain structures, certain structures, and certain, essentially, as we call tiny organs, organelles in them. So a few structures we're going to find about the muscular system is a sarcolemma and the sarcoplasm. So what exactly are those? Well, they are the equivalent of the cell membrane and the fluid within the cell. However, let's pay attention quickly to the word sarco. The prefix sarco literally means flesh. And we're going to see that a lot of the words that we use for generic cells like cytoplasm, well, sarcoplasm, so we should swap out that word to delineate that we're talking about the muscular cell in particular. So sarco means flesh, and like I said, we're going to interchange those words a little bit. So sarcolemma is just the cell membrane, the covering of the cell. Sarcoplasm is the intercellular fluid within the cell. That says intra, but it should be the intercellular. So we need to fix that typo on that. So alongside some of these other structures, we're essentially going to start building a muscle from the ground up. So I like to take the muscle from its smallest components and then work my way all the way to the very end. Now, the smallest component we're going to see technically not there yet, but the smallest unit we're actually going to see is the individual protein filaments outside of molecular structures. So let's talk about a myofibril first. A myofibril is long strands of what's called sarcomeres. And these myofibrils will run the entire length of the entire muscle fiber. So if you actually look here in the diagram, this blue and red striped thing is the myofibril. And that myofibril is just sarcomeres lined up one after the other. Kind of reminds me of, looking at it, and at least in this diagram, kind of reminds me of the like the classic little rocket pops or push pops that you get from the freezer section. So the myofibrils are the threads of sarcomeres that form a chain and run the entire length of the muscle fiber itself. So what exactly is the sarcomere? The sarcomere is what we're going to be paying the most attention to in this lecture. It's going to be essentially the bulk of the lecture and probably the hardest thing to understand out of the lecture. So a sarcomere is the contractile unit or functional unit of the system. And so this sarcomere contains a few sections. So we have the I band, which contains specifically the Z line, or this zigzaggy black line that you see on the diagram right here. So this Z line is where we have a protein filament called actin. We'll take a look at these in a second on the next slide, I believe. So this actin attaches to this Z line, and then which is the red line that you see stretching towards the center. So this actin stretches towards the center where we have the A band in the center. More specifically, this H zone, as I like to call it, the heavy zone, because we have the thicker protein filament, myosin, in that central region, which is going to then reach out towards those Z lines where the actin is. So I believe the next question, let's see, make sure we touched on that. Yes, so what are the different regions, right? We have the Z lines in the H zone, and we do have the two myofilaments. So the myofilaments, aka muscle filaments, myo meaning muscle. So there's another prefix that we want to add to our repertoire. So myo means muscle. So these myofilaments are the individual protein filaments of the muscular lecture. And there's two main ones that we're going to look at. One second. Because this is supposed to be for fast. You're gonna watch this and rewatch it. This is a crash course video. It ain't a full lecture. Because if I did this whole lecture, it'd be like hours. Sorry, I had to like close someone's thing out. I'll edit that out. All right, so the two myofilaments we look at, the main two myofilaments, are the actin and the myosin. Now, normally we label one as thick and one as thin. So actin is our thin filament. As I like to think, act thin. Like, oh, I see someone walking by and you suck in your gut. You got to act thin. So actin is the thin filament and myosin is the thick filament. And as we said, actin is attached to the Z lines, while the myosin is in the central region of the H zone that, well, as we're going to look at eventually, the sliding filament theory are going to pull in towards the center and shorten this sarcomere. So as we said, this sarcomere, so let me just go back to that slide real quick. So this individual single sarcomere measured from the Z lines, right, lines up with, like we said, this myofibril. The myofibril is that chain of sarcomeres. So now as we look at this again, we can see how now you can see the Z line here, right? That's one single sarcomere. So we're just going to put one sarcomere here, and then a sarcomere, and then a sarcomere, and then a sarcomere, and a sarcomere, and we're just going to have a big long chain of sarcomeres all through the individual muscle fiber. So hopefully that paints a good picture for you guys. Another structure we take a look at in regards to the muscle fiber, the individual muscle fiber, is the sarcoplasmic reticulum. Again, very similar to the endoplasmic reticulum of a normal cell. In this particular case, the sarcoplasmic reticulum stores calcium ions to then interchange it between the membranes within the cell that are going to facilitate the calcium pump in the muscular system that helps to produce the contractions of the cell and the shortening of the individual sarcomere. So if you look at this breakdown of a picture of a muscle, this is essentially showing you the Russian nesting doll effect that we're essentially looking at. So if we actually take a look at, and if I can maybe zoom, not too much. So if we zoom in a little bit, right, we can see here's the myofibril, which the myofibril is those chains of the sarcomeres that we looked at, Z line to Z line in the center of the H zone, right? Then we have this muscle fiber, right? This single muscle fiber, which we've already seen, contains the sarcoplasmic reticulum, the sarcolemma, the sarcoplasm, the myofibrils, lots of mitochondria, as you might have noticed in the previous slide, right? So now we want to keep going through the cascade. We want to keep going through the Russian nesting dolls here. So this individual muscle fiber gets grouped up with other muscle fibers. We call this the fossicle. So a fossicle is literally just a group of muscle fibers. So we're essentially going to take the muscle fiber, group it up with a bunch of muscle fibers, and create a bundle called a fossicle. And then we take a bunch of those bundles and group them up together to make the entire muscle. So a muscle is literally just made out of groups of muscle fibers, many different groups of muscle fibers. Now, we do have connective tissue that covers and helps to support and give shape to the individual muscle fiber, to the individual muscle fiber groups, fossicles, and to the entire muscle in and of itself. So the innermost layer, we could consider it, right? The individual muscle fiber is covered by the endomysium. Let's break that word down real quick. Endo means within, the inner region. Myo, muscle, and then sium refers to like a membrane. So endomysium means the innermost lining of the muscle, in this case, muscle fiber. So the endomysium covers the individual muscle fiber. Then we group that up with the fossicle, other muscle fibers to make a fossicle, and then cover that with connective tissue and call that the perimysium, which means surrounding right? In the surrounding muscle fibers and the connective tissue covering muscles, right? Muscle fibers. And then we covered the entire muscle, which is just groups of the fascicles, with the epimysium. Epi means the outer region on top of, right? In this case, right? So you can see how we use endo, peri, and epi to indicate which region, right? So endo is the innermost. Peri usually means surrounding or on the peripheral, and then epi means on top of or the outermost region. And we're actually going to see that endo, peri, epi schematic through a lot of other lectures, like the nervous system, where we'll have the endoneurium, perineurium, and epi or endoneurium, perineurium, and epineurium. So it all kind of lines up very similar there. So the connective tissues that we were just looking at cover and support the individual muscle fibers and groups of fibers and so on and so forth. But that same continuum of tissue then travels past the muscle fiber, creating the tendon. So the tendon, as we've seen before, right, that tendon anchors the muscles to the bone, skeletal muscle in this case. So I should have prefaced that the breakdown that we're looking at is specifically for skeletal muscle fibers. So the myofibrils and all that. We're specifically looking at the breakdown of skeletal muscle tissue. So the skeletal muscle tissue, the connective tissue that supports these individual fibers and so on and so forth, continues on past the muscle fibers, past the entirety of the muscle to create a tendon, which then attaches that muscle to the bone. Now, the place at which the tendon and the muscle meet, so like where the muscle ends and the tendon begins, we call that the musculotendinous junction, right? Fun fact there, I guess. Now, in regards to these tendons and these connective tissues, we do have a few words we can throw out in regards to specificities of different types of tendons. So we have here what's called an aponeurosis and a retinaculum or retinacula. So an aponeurosis literally means a broad, flat sheet of connective tissue that is typically responsible for being like the meeting point between various muscles and bone. So an easy example, as you see in this image here, is what's called the abdominal aponeurosis. So many abdominal muscles will attach to this broad tendon, this aponeurosis, which is then going to anchor all those muscles to each other, as well as anchor it to the bone. Another example of an aponeurosis would be the thoracolumbar aponeurosis, which is in your low back. And then a retinacula is a band or a strip of tissue that typically is responsible for holding down tendons. So as you can see here is your ankle in this image, and this is holding down, in this particular case, the dorsiflexors or the extensors. So this is what we call the extensor retinaculum of the foot. Now, in regards to muscles, there's a few parts of a muscle. So we already looked at the tendon and the musculotendinous junction, which I do believe is a separate slide. But we have what's called the belly of the muscle. The belly of the muscle is actually the central fattest region of the muscle. So an easy example, as depicted in this picture, the biceps brachii is an obvious example of where the belly of the muscle is. When you flex your arm and try to show off the guns, that fattest central region, the peak of the bicep, is the belly of the muscle. So typically it's in the center, but it's usually the bulkiest part of the muscle in and of itself. Now, I will preface this, that when muscles contract, skeletal muscle specifically, when skeletal muscle contracts, it tries to pull everything that it's touching towards its belly, towards its center. And so when we get to kinesiology, I think that is a very important thing to be made aware of and make note of, when you're trying to understand how muscles are working and moving the bones and producing the movements at the joints. Now, in regards to that kinesiology and that same idea, right, we do have some concepts in regards to skeletal muscle tissue, such as origin and insertion, and the definitions. Now, when I teach kinesiology, I try not to get too harped up on, muscle attachment sites too much, but I do have people make sure that they understand the concept of what origin versus insertion is. So to me, it's a bit of an arbitrary delineation, but it makes sense. And when you look at some aspects of it, I can justify it. But the way I explain this, it's going to just kind of, like I said, it's just arbitrary. So the origin of a muscle is the attachment site. So a muscle is going to attach to bones. So it's the part of the body or the bones or attachment sites that the muscle has that are going to move the least. Well, I'll explain that with a little detail in a second. The insertion of the muscle is the attachment site of that muscle that is going to move more. Now, looking at that third line on this slide, when a muscle contracts, it pulls the insertion towards the origin. That one, I just try to eliminate, right? Because in reality, when a muscle contracts, what a muscle is trying to do is, like I just said, it's trying to pull everything it's attached to towards the center of that muscle, towards the belly of the muscle. So let me go ahead and just show you a decent little example. So for instance, let's say the pec muscle, my chest muscle here. My pectoralis major attaches to the clavicle, the sternum, and the lower ribs, some of these lower ribs here, the costals, right? So I have a sternal head, clavicular head, costal head, and then it attaches onto my arm, my humerus here, right? So in this case, the origins here on the chest or center of my body are the origins. The attachment sites here are my origins of the muscle. And then the insertion is here. Because by definition, right, my chest is going to move least, or in this case, really not at all. But my arm, my humerus bone, that is literally just wacky flailing, inflatable arm tube man guy, right, moves a lot. So when my pec muscle contracts, it's going to pull the arm towards all of this here in the center. I can't leave my arm here and try to like yoink my body towards my arm. So that's where the idea of insertion moves to origin comes to play. That's not the sense, it's not the same when for every single muscle, right? Because there is something called functional reversibility, which is, I actually believe on the next slide, functional reversibility is where the insertion can move to the origin. But I try not to really confuse you guys with this, but I'm going to make sure that you're aware that these are things that you might see on your tests. But like I said, it's just, I want you to understand the concept of muscular contraction, and I want you to understand the ideas and the principles behind it, right? Origin is going to move least, insertion is going to move more, right? And the muscle is just going to try to yoink everything together. It's just some things just don't move while other things move a lot. Or both parts of the attachment sites of a muscle can move. It's just if I stabilize one area, it's going to move a lot more. I forgot I wasn't actually displaying the slide there. So, but it's fine. So I'll show you the slide in a second. But to give an example of a muscle that has functional reversibility, my upper trapezius muscle. My upper trapezius attaches to essentially the base of the skull here, without going into detail of all the various insertions, and then out to the shoulder here. So if I stabilize my normally the attachments around my skull and spine are the origins, right? And then the attachment to the shoulder over here is the insertions. So logically, you'd say, well, that means that this part's going to move here. And that is true, right? Because my traps can pull my shoulder up like this, right? But that's me keeping my head in position and using that muscle to lift it up like that. However, if I stabilize my shoulder, this muscle can actually pull my head towards that shoulder. So that's functional reversibility. But in reality, if my upper trapezius contracts completely, it's just going to do this. So like I said, you know, hopefully that makes sense. I know it's muscular contraction is probably one of the more confusing concepts for a lot of people. And it's really going to help you out when you get to kinesiology and start learning how, you know, actions are being produced by muscle contraction. But yeah, you know, just to preface this now, I think might help you guys some. So here's the slide where it talked about the functional reversibility. So if you're writing stuff down, write your notes down, writing the questions down, whatever, there it is. And then enough of that. Moving on to the next thing. So about that muscle contraction, how is this happening, right? So on a molecular level, on a microscopic level, how is this happening? Well, we're not going to get too detailed about everything and all the steps in the process, but that sarcomere we looked at previously is the basic unit of contraction, as we mentioned. So the shortening of the muscle and technically lengthening too occurs there. So we call this the sliding filament theory or the sliding filament model, where essentially through the various steps, as you see in the diagram, which includes the you know, the power stroke and the detachment cycles and all that, the myosin grabs onto the actin and then pulls it towards the center, which then, if you imagine it, right, those Z lines move to the center. And if those Z lines move to the center, then, well, now the sarcomere is shorter. You amplify that along the entire chain of sarcomeres, and you have, you know, a pretty lengthy muscular contraction, right, or shortening of the muscle. So to keep it simple, right, it's the sliding filament theory, sliding filament model is where the actin and myosin, you know, come together towards the center, bringing the Z lines toward the center and creating the shortening of that sarcomere. Now, one of the main muscles, or excuse me, one of the main molecular structures responsible for producing muscular contraction is the molecule called adenosine triphosphate, which that means we have one adenosine molecule and 3 phosphate molecules. Now, I don't want to get into the super sports science of it, but I'll preface this, that we take that molecule, we then take that, we take that molecule and we break off one of the phosphate molecules, which then allows all this stuff to happen, creating it. And so the byproduct of that is adenosine diphosphate, and then we got to rephosphate that molecule, and, you know, then we get into a whole big sports science, you know, spitball. But just to give you guys at least a little bit of information of, you know, what that adenosine molecule is kind of doing, right? But yeah, so that's muscular contraction at its you know, tiniest structural unit, the sarcomere. So now, of course, this muscular contraction doesn't just happen all willy-nilly, right? All these muscular contractions, the entire body is essentially controlled by the nervous system and, well, technically also the endocrine system. Combined, we call that the neuroendocrine system. So our nervous systems, especially for skeletal muscle, right, is going to tell it how to contract and how much to contract and all this stuff, right? So the nervous system has to reach out and touch and talk to the skeletal muscles. So we call that the neuromuscular junction. The neuromuscular junction is literally just where the nervous system meets the muscular system. Now, there are different parts of what we call the neuromuscular junction, which I think is just, I just have it. Okay, yeah, it's just for the picture, right? So if we actually take a look at this picture, when we get to the nervous system lecture, we're going to see that there's different types of neurons, nerve fibers. In this particular case, what's reaching out to the muscle for the neuromuscular junction in this regards is what we call a motor neuron. A motor neuron is responsible for causing change or producing motor output in the body. So this little telodendrite of the nervous system reaches out and comes towards the sarcolemma. So we have what's called the synaptic bulb. So the little ET finger looking thing trying to touch the muscle, right? That big fat part is called the bulb. So this bulb reaches out to these folded sections in the sarcolemma that you see called, I guess I can use my cursor, called the motor end plate. Now so it's kind of like that. You ever been riding in the back seat with your brother or sister and you guys are antagonizing each other and it's like, I'm not touching you. So this synaptic bulb doesn't actually physically touch the muscle. There is a gap, and we call that the synaptic gap, where we then pass these molecular neurotransmitters across that gap to then bind to receptor sites in the sarcolemma, which then tells the muscle to do things. Now, I will also say this, that the neurotransmitter that you're seeing in this image right here is what we call acetylcholine, which is the primary neurotransmitter of the nervous system to facilitate the process of muscular contraction. Hopefully that was not too much. Oh, perfect, right? What is the neurotransmitter responsible for muscle contraction, right? Acetylcholine. So if you needed the spelling, there it is on the board there, acronymed ACTH. So two molecules that we want to remember so far in regards to muscles contracting: adenosine triphosphate and acetylcholine. So let's take a look at some other components and concepts of the muscular system, namely a motor unit. And I think this is really cool, interesting stuff. So what exactly is a motor unit? Well, a motor unit is, well, a single unit that is made up by the individual motor neuron, right? And all of the different muscle fibers that individual unit reaches out and touches to. So you actually can see a decent little example in this picture of what we were just looking at with the neuromuscular junction, how we have a single motor neuron, single little branch that then breaks off into all these little telodendrites that then touch a bunch of different individual muscle fibers and controls them. So that group, that block, is the motor unit. Now, a muscle can have thousands, depending on its size, motor units. And we call the totality of motor units the motor unit pool, or motor pool, I guess is called, right there and on that. So what does this matter? So we'll touch on the all or none law in a second, but essentially your muscles are very strong and powerful and capable, and that your muscles can produce forces that you didn't even think you were able to produce. So maybe you've heard of stories of people doing superhuman feats of strength, lifting cars and boulders off of children and stuff like that, right? I mean, your body, your nervous system limits your body in an effort to protect itself, because, you know, obviously if we lifted thousands and thousands of pounds without actually being able to, you know, we're going to severely have some repercussions. But motor units get recruited. I think it's actually on the next slide. Yeah. So motor unit recruitment is the activation of certain units, and specifically enough units to produce the activities in which we're trying to perform. Now, all through your life, I'm gonna go zoom in here. All through your life, from even in the womb, right? Your nervous system, your body has been calibrating and learning things. And specifically, you're like a mini physicist. So you, especially after you've been born, you are now in the real world, right? And that your body is now out of the embryonic fluids and all of that, which technically is kind of creating like a zero gravity environment for you. So now as a child, you're learning how to use your body and move through space and gravity, and you're used to, now you're learning about these physical forces, and like all through your life you're trying to calibrate throughout this process. So if you look at a child, as they start growing, like let's say like a toddler, they're just wild and moving and doing all these crazy things. I can't flail my arms too much, but smack this man in the face. But you're doing that as a child because you're actually learning, like you're learning the boundaries of your body, you're learning physics, you're learning weight versus gravity versus distance and power and speed, right? So it's like, you see a kid pick up a rock and just chuck it across the yard, because it's learning how all this interrelates to each other. So you're always doing this process. Your nervous system and body is always calibrating how much work needs to be done to do certain things. Now, an easy example of this is like your backpack, right? You're all students here, or ladies, your purses. You instinctively know how much your purse or backpack weighs, even if you didn't have a number on it. More specifically, your body knows how much muscle effort it needs to utilize in order to pick that up and move it, right? So let's take your backpack, right? You put your backpack down and you walked away, and then I came in and took all the books and stuff out of it. And you go and you grab your backpack, expecting it to be maybe 10 pounds heavier than it was, and you go, whoop, like, whoa, that's really light. So you added extra effort than you needed, and you see how easy it was for your body to overdo that activity. Or if I put bricks in your bag and you try to grab that bag and you're like, right, and you stutter a little bit, right, because your body has to now recalibrate for like how much weight, how many motor units do I need now for this? So I think that's a really cool, interesting concept, especially when you get into like sports medicine. Is very interesting to understand how motor unit recruitment can really help with hypertrophy, stuff like that. I think it's really cool. So let's go back to the slides. We did skip something real quick though. We have what's called the all or none law, which is more related to the nervous system. So the all or none law talks about at which point. So when we talk about stimulus threshold, and at a point in which a stimulus is recognized, and that once a stimulus is recognized and a response is produced in regards to that response, or the output by that nerve, and in this case the muscular system as well, is done to its fullest capacity. So essentially, like, either the stimulus is strong enough to trigger a response, and then we do that response with no hesitation, or the stimulus isn't strong enough at all and we do nothing. So that's kind of the premise of the all or none law. So we'll see that again kind of in the nervous system, nothing too crazy about that. As we already answered this before, what is the molecular unit of energy for the muscular system in this case? Adenosine triphosphate, ATP. Yeah, you know me, we be muscle contracting. That's actually the molecular structure if you needed to, I don't know, look at that. We see here what's a thing called myoglobin. Myoglobin is an iron-based protein inside the muscle, very similar to the hemoglobin inside the actual red blood cells. So this obviously helps to store the oxygen for the muscle, because if you didn't know, that muscles need lots of oxygen in order to go through their certain cycles, such as aerobic cycles, glycotic cycles, and stuff like that. So we always want to make sure we have a good supply of oxygen to pump back into those muscles. So with that in mind, now we're going to get into a very interesting concept, again, also for sports science and things, but also helps Doesn't help us at all, actually, as massage therapists, if I had to really explain and think about it. But hey, it could be on your test, and we're going to talk about it. So, muscle fiber types. Now, there's lots of muscles, or excuse me, lots of muscle fibers in a single muscle, and those fibers themselves can be differentiated for specific roles. So, in the generic classification, we have two types of muscle fibers, type 1 and type 2. So type 1 muscle fibers, what are they responsible for, and what kind of twitch fibers are they? Well, type 1 muscle fibers are known as red muscle fibers or slow twitch muscle fibers. So going back to the myoglobin, right? These type 1 muscle fibers are red. Why? Because they have a higher concentration of myoglobin, which means they have a higher concentration of oxygen reserves. And if they have a higher concentration of oxygen reserves, then they can produce movements or activities for longer stints of time. So we typically call or consider type 1 muscle fibers to be a postural muscle fiber. So as we learned already, maintaining posture is that constant contractility, partial contractility, tonus of the muscle to maintain position. So in this particular case, type 1 muscle fibers, they're slow to react. That's why we call them slow twitch, but they maintain their contractions for longer periods of time and can produce these activities for longer periods of time. So we often liken the type 1 muscle fibers to marathon runners, right? Because a marathon runner is someone who, you know, or like an Ironman, right? You gotta swim, you gotta bike, you gotta run, you gotta do all these things. So you need to have energy reserves. You're good, you can grab some. So you have to have all these different energy reserves for it. And then interestingly enough, type 1 muscle fibers are usually a little more activated for super heavy lifting and they're actually smaller, which is interesting when you get into like hypertrophy training and stuff like that. But type 2 muscle fibers, though. Now, as you can even see in this diagram, there's 2 listed types of type 2 muscle fibers, but I'm aware of 3, and I think they're still finding more, and I think there's like 4 or 5. So we have type 2A, type 2B, and even type 2X, and I think there's a type 2C or something. But so what's the difference between type 2 versus type 1? Well, pretty much the opposite, right? So in this case, type 1 was slow twitch, type 2 is fast twitch, and type 2 happens to be what we call white muscle fibers. Why? Because these muscle fibers require or just don't have as big of a store of oxygen as they do the type 1s. So these particular muscle fibers are what we call the like phasic muscle fibers, or the sprinters of the muscle, because they are meant to produce very finite, intricate movements and then stop, and that's it. So like a sprint, right? I dash 400 yards, 400 meters, whatever, and then stop. That's it. I'm done. I'm tapped out. So these muscles will activate and then just stop after a certain amount of time, and then that's it. Now, the difference between type 2A and type 2B, it's, you don't need to know any of that, but it's just basically like the different contractile and length of life, essentially. But we'll give you a couple things to think about. One, type 2 muscle fibers are bigger than type 1, which usually matters if you're trying to make your muscles look bigger. But also, type 2 muscle fibers, as we said, are phasic. So let's go into those words real quick. Postural versus phasic. I guess I'll just zoom in on my face. So postural muscles, as we said, are largely responsible for maintaining posture. Phasic muscles, think if you like phase through a wall, well, you moved through the wall. So phasic muscles are more responsible for intricate, finite movements. So just to briefly explain the roles there, or the idea is that first and foremost, every single muscle in your body has a composition of all those different types of muscle fibers. It's not like one muscle has all of these, one muscle has all of these, right? They're very intermingled, but the quantities change depending on the muscles. So for instance, your deltoids are largely phasic muscles and are going to have a higher concentration of type 2 muscle fibers to do the finite movements of the shoulder and then be done, and that's it. Whereas the erector spinae muscle group of your back keeps you upright literally, I mean, all day until you go to sleep, basically. So those muscles are largely or have larger quantities of type 1 muscle fibers. So, I mean, it just makes sense, right? I can stand like this a lot longer than I could hold my arm out like this. I mean, after about 30 seconds to a minute, you're already like, oh my God, this is burning. I need to put my arm down. So, basically just don't think that, you know, one muscle has this type and then that type and this, that, and the other. But we do classify some muscles as largely postural versus largely phasic. So typically the big muscle groups that are responsible for holding us in position, like erector spinae muscles, are postural. Quads and hamstrings are generally postural. Calves are generally postural, right? Typically other muscles are like my leg muscles specifically, right, are usually postural because, you know, standing requires a lot. But like a lot of the muscles in my arms are probably more phasic, right? So on and so forth. So little tidbit there. So let's get back into this here. So when it comes down to the muscle contraction, this is a really big concept too. I really want you guys to make sure you learn and pay attention to this very well, because this is going to be relatively important throughout the entire program. And, you know, you're going to see a lot of questions about this. Why? Because sometimes this concept comes up in the assessment type questions, or even, you know, like the benefits or, you know, guidelines questions sometimes. So isotonic versus isometric contractions. Right now we're looking at the isotonic contractions. So what exactly is an isotonic contraction? An isotonic contraction is when a muscle is contracting and the length of the muscle is changing. So that is the specific definition there, that the muscle is generating force and the length of the muscle is changing. Now, if a muscle is changing lengths, then, well, it can change lengths in one of two directions, right? We can either get shorter, or we can either get longer. So let's say my bicep muscle. If I stand out normally, my bicep muscle in its full length, this is in an eccentric state, which I guess I should probably explain to you what concentric versus eccentric is, right? So this is an elongated state, in an elongated state. Dang, that was a tongue twister. So when my biceps muscle contracts, it's going to pull my elbow like this and pull my forearm like that. Now, that means that the muscle is contracting or getting shorter. We call this phase of the movement the concentric phase, or as you can think of it as the contraction, right? Very simple. Contraction, concentric. Muscle gets shorter. Concentric, contraction, muscle gets shorter, right? You can just make that a rhyme. Now, when the muscle lengthens out, that's the eccentric phase, or the elongation of the muscle. E and E, eccentric elongation. Now, in sports science, there's another phase called the amortization phase, which you probably don't need to know that as a massage therapist, but the amortization phase is the brief pause as those two phases change in between each other. But, you know, whatever. And also in sports medicine, the concentric phase is known as acceleration, and then the eccentric phase is known as deceleration. So accelerating the movement and then decelerating the movement. So the isotonic contraction, which I can also break down the word, right? Iso means the same, tonic means the same tone. So this means that the tone of the muscle is relatively staying the same throughout the movements and changing length of the muscle. Now, if we look at the so isotonic contraction, right? the muscle is changing lengths, and it changes lengths in one of two ways. It either gets shorter via the concentric phase or contraction phase, or it gets longer via the eccentric phase or the elongation phase. Now we have what's known as the isometric contraction. So isometric contractions, right? You probably heard of isometric exercises at the very least. And an isometric contraction is where the muscle is activated and contracting, but the length of the muscle stays the same. So again, so we kind of explained the definition just a moment ago. So isotonic meant the same tone of the muscle throughout the movement. Isometric means the same length of the muscle. The muscle stays the same length. So right now, just maintaining posture, everybody is maintaining isometric contractions, right? For the most part. Now, you can think of like an exercise. So if you think of a very famous isometric exercise that people usually know and hate, a plank, right? If you're holding a plank, right, your abdominal muscles are engaged, but you're not contracting them like you're doing a crunch. They're just activated, but not moving, right? So isometric means that the muscle's activated and not changing length. So then we have the different classes of levers, which the AMBLEX says we need to know it. I think it seems a little bit unnecessary, but first and foremost, classes of levers are based around what's called a fulcrum, a load, and a pull. The fulcrum is the pivot point and is usually the joint where the movement occurs, basically. The load is the weight in which we're trying to move, where the pull is the force used to move that object. So our class 1 lever is where the fulcrum is situated in the center. If you can look at the image there, the fulcrum is situated in the center and the load and pull are on either side. So resembling a seesaw. And the easiest example is essentially anything along the spine, because our spine, right, our spine maintains the center line, right, the fulcrum in the center, and then we have muscles on either side to either pull us forward or pull us backwards, defying, well, our weight and gravity and so on and so forth. So class 1 lever, probably the easiest, right, the seesaw. Class 2 levers resemble a person carrying a wheelbarrow, and as you can see in this image here, is exemplified by your calf muscles. So in this case, now we're moving the fulcrum to one end of the spectrum, and in the center is the load, while the force to move that load is at the very end. So very similar to the wheelbarrow. So the fulcrum or pivot point is, in this case, the wheel of the barrow. Then we have the dirt or whatever objects that are in the actual barrel of the wheelbarrow. And then we have the guy lifting up, or woman, whoever, the person, right, lifting up that other end of the wheelbarrow. Just like your calves would be lifting up your weight, because your weight is dead center of the ankle. Your tippy toes is what you're trying to stand on, are the fulcrum or pivot point, and your calves are pulling at the back of your heel, which is right behind the bulk of your weight. So, calves. And then our class 3 lever is, similar to like you see here, the bicep curl, or a person, shoveling something. So in this case, the fulcrum is on one end of the spectrum, just like in the previous example, except now we're reversing the load and the pull ratio. So in this case, the load is usually furthest away and the pull is in the center. So just like the shovel there, we can see that the person pivots and wrenches in the back, right? There's a little example here, right? So we have that little wrenching action here. This is the fulcrum where I can pivot it. This is the pull where I can use muscular effort to lift it up. And then I have the object on the other end that I'm trying to move. So that's class 3. Like I said, I probably wouldn't pay too much attention to the classes. But I think as long as you just have a general understanding of what it is and you can give it a short example, like literally if you just remember the pictures like that, you should be a-okay. So we do have the different classifications of muscles by their shapes, right? So here's a few examples. And this, again, this is skeletal muscle tissue. We're largely talking about skeletal muscle tissue throughout this entire program in general, but also in this chapter. So we do have what's called parallel, or also known as fusiform muscles. Well, we all know what parallel lines are. They don't intersect. They run side by side and they run straight. Or we call these muscles fusiform because they're in a fused formation, I like to call it. So easy examples would be like your rectus abdominis, right? Your abs. These muscle fibers run vertical and they run side by side. Then we have convergent muscles, which, well, if you were to converge with someone or something, you would meet at a specific point. So, and you guys came from different places. So you started broad and wide and came to a finite point. So much similar to your pectoralis muscle, pectoralis major specifically, it starts broad. As we saw in my earlier example, I had shown you that it touches the clavicular. We had a clavicular head, sternal head, costal head, all that, right? So very broad, wide attachment site to then reach to a very finite point on my arm. Then we have spiral muscles. Spiral muscles wrap around the body. And that wrapping around the body is produced by, in this case, the lats. The lats literally come from, I guess I could show you. The lats literally come from your low back and then wrap all the way up through your armpit and then attach to the front of your arm. So they literally wrap around your body like that. So they're spiral muscles. So then we have circular rings of muscles, right? Well, circular muscle is just a ring of muscle, and we often call those sphincters. Now we're going to see lots of sphincters throughout the gastrointestinal tract, the digestive system. But the easiest examples, two sphincters, would be your mouth, right? The orbicularis oris, and then your eye, right? The orbicularis oculi. So those are sphincters. They close and they cinch shut there. Then we have, lastly, pennate muscles. Pennate, I think like penne pasta. You know how it's got like that little angle cut on the penne pasta, right? Well, pennate is probably the most complicated because we can have unipennate, bipennate, or multipennate. So basically, a pennate muscle is where we have a central tendon and then we have muscle fibers branching out to the sides from it. So the easiest way to think of it is a leaf or a feather, right? And a unipennate would be if I took the feather and cut it in half at the the center of the feather, right? Or if it was a leaf, I cut it at the center where the stem is, right? That's half of a bipennate structure. So bipennate in this particular case is where we have the central tendon and then the muscle fibers branching off to the sides, just like I said, very similar to the feather. So, and then lastly, we have multipennate where we have multiple tendons and muscles branching off of those. So examples of a unipennate would be like your fibularis muscles, the muscles that are, on the lateral side of your lower leg. And then bipennate muscles, this one I specifically want you to remember because I do remember seeing this pretty widely, explained and questions on it. A bipennate muscle would be your rectus femoris of the quadriceps muscle group. Make sure you remember that. And then multipennate would be your deltoids. So then we have this. This will be our last slide, actually, of all of the slides. The rest are going to be pathologies, and I'm not going to go into the pathologies because I already recorded all the pathologies. But our last slide here is about the roles that muscles play in regards to movement. So let's just go ahead and lay it all out, and then I'll explain it. So in the realm of roles that muscles play, we have a prime mover, we have synergists, we have fixators and stabilizers, and then we have an antagonist. A prime mover is also known as the agonist. Try not to confuse that with antagonist. Agon, A-G-O-N-ist, whatever. Agonist is also known as the prime mover. This is the muscle most responsible for producing the movement. Again, I'll explain this in a second. Synergists. Synergists do the same thing that the prime mover does, but just not as well. Fixators and stabilizers help to keep the joint secured during the movement. And then the antagonist does the exact opposite. So let's go ahead and zoom in on my gorgeous face here. So let's give some examples here and then talk about it. First, let me paint a picture. This orchestra is like we're trying to create a movie, right? And if I wanted to make a new Batman movie, because we need all the millions that we have, right? Well, I have some roles I need to cast. Obviously, the star of the show is Batman, right? He's my prime mover. He's the star of the show. He's the most responsible for the plot of the show, of the movie. Then I have a synergist, someone who does almost the same thing as Batman, but just not as cool. So there's Robin, exactly, right? Robin, And then we have to have the general cast, right? People who, make the story cohesive, right? So the general townspeople, Gotham City Police, right? Those are the fixators and stabilizers. And then what's a movie without a Batman? What, I'm going to make a movie about Batman how am I going to make a movie without a bad guy? Is my movie just going to be Batman and Robin eating some Cheerios? Like talking about their day, going for a stroll in the park? Maybe. Be a terrible one probably, but no, we got to have a bad guy. So and then we got the Joker, Riddler, whatever else people piss off Batman, right? Insert those people. So the idea of this though is that we casted the roles for their specifics, right, based off of the plot of the movie. So the plot of the movie was Batman kicks ass, I guess, whatever, right? Now, what if the plot of the movie was the Joker rises, right? So in this case, I want to make a movie about the bad guy, the Joker. Well, now I want to make sure that the Joker is the star of the show. So the Joker is my prime mover, the star of the show, right? And then, I don't know, Joker and Harley Quinn, right? She's my synergist. And then, same thing, I got like Gotham City Police, fixators and stabilizers. Usually those roles don't change. And now my antagonist is Batman and Robin. So why did I explain it like that? Got to wet the whistle. Why did I explain that like that? Because the most confusing thing about this is people tunnel vision and think that if one muscle is the prime mover, it's always a prime mover. So people try to go on this crusade and say, well, what is this muscle the prime mover? Is this muscle a prime mover? I'm going to tell you this. Almost every muscle is a prime mover that is largely responsible for producing a movement. It's all dependent on the action in which we're observing, just like the plot of the movie. Depending on how the movie, the design of the movie, the roles change. So the easiest example is the elbow, right? The elbow does one of two movements. It either flexes or it either extends, right? And so if I'm going to make the cast of characters for this, then my roles are going to be whatever, right? So in this case, if I'm going to make a movie called Flexion of the Elbow, sounds like Phantom of the Opera. It probably worked. Flexion of the elbow. My star role is biceps brachii. My biceps muscle is mostly responsible for flexing the elbow. But he's not alone. I also have brachialis, which is a smaller muscle underneath biceps that also flexes the elbow. Then I have fixators and stabilizers, usually forearm muscles, whatever, we won't list them all. And then, of course, I have my antagonistic muscle, the triceps, because my triceps does the exact opposite action. So in this case, my biceps muscle was the prime mover, right? Only because I was observing specifically elbow flexion. Now, if I was trying to observe elbow extension, now my triceps is the prime mover and my biceps is the antagonist. So hopefully that kind of breaks the like the third wall of it, because like I said, the biggest issue is people just like get into this crusade of like, oh, you know, what's a prime mover? They try to make a list of what muscles are prime movers, and it doesn't work. It's like I said, it's just based off of whatever you're observing at that time.
In that scenario that you just had, what would be the fixator or the stabilizer?
Like the forearm muscles. I mean, there are tons of them, so I'm not going to list them all. But
thank you.
But that, yeah, no problem. But yeah, that's the muscular system lecture. So if I had to do just a quick recap, you know, what do we really want to take out of this? One, make sure you know the roles of the muscles, right? You know, what is the responsibilities of the system? You know, that goes for every physiological system. Why do we have this physiological system? What is it doing for us? What is its major components? Where are they, and what do they do? So in this case, right, the muscular system produced heat, produced movement, maintain posture, right? Skeletal muscles are made of their basic units, right? So we take the myofibrils, right? The actin and myosin. Actin is the thin, myosin is the big. We take those together to make a sarcomere. Sarcomeres are measured from Z line to Z line with the H zone in the center. Actin on the Z lines, myosin in the center. We do the sliding filament theory model, right, to bring those Z lines to the center to create the shortening. So we're going to take that single sarcomere, the functional unit of the system, make a big long chain of them called myofibrils, take a bunch of those myofibrils and put it in a muscle fiber. We're going to take that muscle fiber, we're going to bundle it up with other muscle fibers to make a fossicle, right? We're going to cover the muscle fiber first in the endomysium, and then bundle that up with a bunch of muscle fibers to make the the fossicle, and cover that with the perimysium, and then take a bunch of fossicles and make a muscle, cover it with the endomysium, right? And I mean, insert all the other little stuff. Honestly, I think that's like the biggest part of the lecture. Oh, and the contractions, right? The isotonic versus isometric. So remember, isotonic contractions. Isotonic contractions are where the muscle fiber is changing length. We have the concentric phase and the eccentric phase. Isometric is where the muscle is contracting, but the length of the muscle stays the same. Also, what other things did we talk about? We talked about, to recap, the different types of muscle fibers, type 1, type 2. Type 1, slow twitch, red, more oxygen, longer length of contraction. Type 2, less oxygen, white, pale, right? Think if you didn't have oxygen, you'd be, pale, right? And do contractions for shorter periods of time, but more responsible for movement. Knowing the difference between postural and phasic, big thing, right? Postural maintains posture, phasic usually is involved with micro movements. And question?
Concentric is the same thing as extension?
No, concentric is the contraction or shortening. So if I was looking at my bicep, concentric, contraction, shortening. Eccentric, elongation, lengthening.
Isotonic.
Yeah, those are within the isotonic. Yeah. Well, I guess I'll stop recording and then I'll edit that later.